So actually, we should now continue with the scientific program. So it's a pleasure for me to introduce Alexei Semenov. And I've seen from his webpage that he has won many grants, he has many publications, and he has also done some serious contributions to the education, which is also quite important nowadays. But today he will speak on definability theory, new trends and open problems. So please go ahead.
So thank you very much, and thank you very much, organizers, for inviting me with a kind of last call, and also to the participants. Specifically, I would like to say that I'm very glad to see my many old friends and some new for me faces, especially to say to thanks Anatol, because he saved this 15 minutes of time for people to relax a little bit. And I don't feel so guilty to being the last and extra time speaker today. So I'll start with a quotation from Alfred Tarski. That's exactly about my topic today. And Alfred said that mathematicians in general do not like to operate with the notion of definability. The attitude toward this notion is one of distrust and reserve. Sometimes, Alfred Tarski was speaking very kind of eloquently. So my talk, my goal of my talk today is continue to changing this attitude. I believe it changed after '86 when it was written by Alfred Tarski, and to ask you to pay some more attention to this field of research. And the most important thing is to start a joint composition of the list of open problems and to solve them. I believe there are many problems which are really interesting and understandable enough and of broad interest in this field.
There might be a question with your talk. We only see your first slide. Are you still on your first slide?
Oh, so that's really bad. No. Is it changing?
Not yet. Well, at least I only see the first slide.
No.
Perhaps nobody. Okay.
That's better. That's slide number 2.
Oh, now it appears.
Okay. Thank you, Max. So here is the quotation of Alfred Tarski. You can see this. And I claimed also the major point of my talk today, that more like open problems that presenting some ready results. But there will be some results anyway. Okay. Is it the portrait slide, right? Okay. So actually, the topic was very popular on the turn of the last century. In the end of 19th century, great figures of our field of mathematical logic and mathematics in general were very much involved in what can be called definitions. So such people like you can see here, Italians and Germans, were discussing what is the best set of primitive notions for geometry and analysis arithmetic, and asking how to define other notions through this one. There were some deep, profound ideas expressed by all these great people. So coming back to the very general perspective, I would say that what are the basic notions of our science, our field of mathematics? It's of course truth, proof, computation, and definition. I think the definition is on the same level of importance and genericity as other things I mentioned. What the main notion, which is pretty evident, but nevertheless, I just recall it. Let's have some universe domain, U, and any kind of logical language. But for evident reasons, we use what could be called logic of relations. So we don't use functions or operations. We use relations only. We can call it simply logic of relations or first order predicate logic without functional symbols. Let's have one relation and a set of relations, a countable set. We call R definable through S if there is a formula which is interpreted as R if we interpret some finite subset of S with extra logical symbols of L. It's pretty standard definition. Then we can consider a closure of set S as all definable relations in this sense. Then we have closed sets with this closure, and we can call this definability spaces. Could have different names. Some of the synonyms of this used in the literature is reducts. We don't like too much the word reduct because it means that it's reduction of something, that we have some original set of symbols, for example, then we have some shorter list. We have some plus and minus and multiply and divide, and then we reduct it to say plus and multiply. So we prefer to start not in a different way, but essentially all the literature on reducts is what we are talking to discuss today. So on this definability spaces, we have a partial order, and evidently we have a lattice, a complete lattice of this, with standard definitions of union as closure of set theoretical union and intersection in evident ways. So if we have a structure, we have all spaces of all subspaces of its space, and so we have lattice of all these subspaces. We can call it definability structure. In fact, we like this set of notions because it's kind of coordinate free. It's invariant on how we choose the signature of a structure. What is important is the set of relations which are definable in this structure, not actually the specific set of names or specific set of primitive relations. So the basic example, something with what everything was started here. The well-known American mathematician Edward Huntington in 1935 described three relations. One was linear order. Then we can define through linear order something different, which is called between linear order, written here in a strange way, but it doesn't matter. It's of course two arguments, x1 and x2. So between means x2 is between x1 and x3. It doesn't matter what was the relation between 1 and 3. And then a cycle. You can see this here, kind of clockwise cycle, x1, x2, x3. Separation, I will not write here the full formula, but essentially it means that segments with endpoints x1, x3, and segment with points x2, x4 intersect. So they're kind of linked to each other. And equality. So we have now, as you see, 5 relations. First is linear order, and then between cycle and separation. And of course, there is a equality. We can assume that all our spaces contain equality also as an element. So first of all, you can discuss that one of these relations can be defined through another. And in fact, there are some relations between these relations. But it was much more harder question. Is it everything which can be defined through linear order in some essential sense, which was clear from the previous slides? Claude Frenet in 1965 proved that there is only 5 of these elements. So if you have a rational line of rational numbers and inequality less in rational numbers, there is nothing else essentially different from these 5 entities: linear order, between, cycle, separation, and equality. This fact was rediscovered by many other authors later. Not time to discuss it. And the real lattice looks like this. There is a maximal element order, and there are two elements below between and circular. Then separation is smaller than both of these, and equality is the smallest one. So this is a 5-element lattice. Actually, that's a question for the audience to think a little bit about this question. If you add just one constant, 0, to rational numbers, perhaps there will be many other relations besides these 5. So how many? Of course, somebody could know the answer, but it's the question to these participants who don't know. What is your estimate for this? Later, I will tell the answer. So the next case, also interesting, is connected with the very idea that rational numbers are very important and, in fact, very simple, of course, set in the model theoretical sense, especially in this with this notion of definability. So rational numbers are homogeneous, means that if you have a finite subset of, say, 10 elements of Q, then and they're in some order. This is less, this is smaller, etc. And then you transfer this to another 10 elements with the same relations of order. Then you can extend this transformation into the automorphism of the whole rational number set. And the notion of homogeneous structure is very important on this level of model theory. And another interesting homogeneous structure is what is called a random graph. I will not give you the exact notion, but well, Simon Thomas in '91 tried to find what are the elements of the structure here. And actually, it happened that there are 5 elements as well. The definition of these elements are here, and the picture is roughly the same as we saw in the case of Q. So the next situation was that there is another also very natural random graph. It's a random tournament, which is also universal like the random graph in general. And we have also 5 elements with that, the lattice of subspaces. The next result is for the random partial order. There's this definition here in kind of also natural homogeneous structure. So it looks like, 5 and 5 and 5, strange, interesting, but not so much. So let's consider some other situations. Simon Thomas, a little bit later than his first work, considered what is called Hansen graphs, a graph which has no full subgraph of n vertices. So it happened that Hansen graph ever has 2 elements of this lattice, trivial only. So that means the maximal and equality. Agarwal has considered generic directed graph, and also some universal object, and it has 11. Yeah, becomes more interesting. Thomas considered hypergraphs with hyperedges, and 2 in k plus 1 looks pretty regular. And some other spaces, for example, this kind of binary tree analog to rationals, non-homogeneous structure, but you can find another system of generators to make it homogeneous. And Badersky, Williams, Pinsker, and Pongratz consider this and get 3 three spaces. So then a little bit more interesting, the same authors, Badirsky, Pinsky, and Pongratz, in 2013 considered random ordered graph, kind of superposition of rational order and random graph, and just two spaces which generate the overall space. So the answer here is 44. Actually, their paper, because of some nice coincidence and humoristic reasons, is called 42, but in our sense it's 44. Okay, so now let's consider the situation with a constant. If some of you tried to guess what will be the answer from rational or with zero, so perhaps you guessed you have a right guess. It's 116. So if you add one constant to rational numbers, and still there is a relation of less, so you have 116 subspaces in this space. If you add an irrational cut, like pi or square root of 2, you'll have 53 subspaces in the lattice. People were trying to do something with this kind of irregularity. For example, Pongratz, the Hungarian fellow, wrote on this. A negative result is a random graph with a fixed constant with one point indicated, and the author he was a kind of PhD student with two collaborators, gave up after 300 reducts, 300 subspaces. So perhaps a way further here could be used kind of computer algebra, try to manipulate with these objects with the computer technologies. Thomas, I mentioned him a couple of times. In his very first paper on 91, formulated a conjecture that every countable homogeneous structure with a finite relation language has finite definability lattice. Which I a little bit reformulated his statement, but essentially it's like this. So all the lattices with the homogeneous structures are finite. And not too much in the general sense was discovered or recognized after this, but many cases, many examples were given. All these cases actually give us examples of finite lattices on the homogeneous structures. So coming back to the very beginning, it's clear how to define, how to find out definability of something through something, just defined, but how to prove impossibility to define. If you give this question to students, in some cases, they actually, after a while, come to the same idea how it was used in other cases of impossibility, like in Galois theory. And so you need to find some transformation, some automorphism, which preserves something and not preserve something else. And in fact, it fits nicely into what's called Erlanger program of Felix Klein. And we arrive here to something which can be called geometry of logic, like in this Galois theory. Let's map any definability space to a group of to the group of its automorphisms. Call it gamma S. And then we have what is called, you can guess, Galois connection, which is a kind of anti-homomorphism between definability spaces and supergroups of the automorphism of the structure. So if you have smaller spaces, you have bigger group of automorphism. What is written here down the page? And for omega categorical structure, you have even isomorphism here. Not homomorphism, but this Galois connection is isomorphism. And it was proven by Rilnadzhevsky, Engler, and Svenonius independently in the end of 1950s. So these two lattices, lattice of subspaces and lattice of over groups, supergroups, are isomorphic. And so it not in the general case when there is homomorphism only. And so to prove that really you have these 5 elements, for example, in rational order, you can find automorphisms of some of them. For example, you can interchange 2 pieces of rationals, or you can revert the rational numbers. In the random graph, you can have complement to the graph, and it's extends to some kind of automorphism of the whole graph, etc. So this is nice, and so then the natural quantum question arises. So what's happening beyond homogeneous situation or omega categorical situation? And that's the issue of our second part of my talk. So first of all, in homogeneous structures, finitely generated homogeneous structures, you have the quantifier-free logic. So you actually don't have too much first-order logic at all. Any sentence is equivalent to just Boolean combination of the some generators. So the natural question, natural notion arises, which is quantifier height of a space. So what is the minimal number of quantifier which can be used to create any relation in the closure of finite set of relations? And you can investigate this in different situations. Also, you can consider different options for the language. We fixed first-order logic as a language, but you can consider, for example, quantifier-free in any case, not homogeneous only, or you can consider what's called existential, and etc. So there are some problems here, and for example, Juncker and Ziegler asked, is the zero height invariant? Means if you define something quantifier-free with some set of generators, will be the same for any other set of generators. At the same time, an interesting issue is, can you have an infinite layers of quantifiers? Of course, it's well known that yes, if you have some arithmetics with plus and multiplication, of course, this hierarchy is infinite. So, but can you have finite hierarchy? So we, with my co-author of this talk, Sergei Sopronov, discovered, yes, this is possible. For any natural number, you can construct space with that level of height of hierarchy. So means that if you add more and more layers of quantifiers to have more and more elements of the space, it extends up to any fixed number. If after say 100, it stops, no more relations appear. But at the same time, if you consider simple structures or simple spaces, it's not easy to find a natural example of this hierarchy. It's a level 4, for example, or even less, even that level like 2. So natural question arises: can we have actually automorphism? Can we have equivalence between these two lattices, like we have in omega categorical case? How we can reformulate to another cases? And actually, a very important theorem here is Theorem of Cerinonus. I mentioned Cerinonus theorem for omega categorical case, but the really important theorem here in this field is Cerinonus theorem. It says that, of course, it can happen that there is not enough automorphisms for original structure, but you can have an elementary extension of the structure for which you will have really the isomorphism. You can, in our kind of metaphor of geometry of logic, you can say that you add some imaginary elements to the original structure, original space, and you have some more imaginary elements, which makes this elementary extension of it. And I just recollect that we started with geometry, so it's more the nature of the TTPs here. What was said about this result, actually very fundamental result of Cerinonus, was written, for example, and Richard Buchy and his student Danhoff in 1973. Observer, upon reading the papers of Tarski, might have wondered about the existence of general theorems which would explain elementary definability, as the above theorems explain the basic properties of elementary logical consequence. And with the appearance of Klein-Erlanger's program in 1872, it became apparent that automorphism groups are most useful means of studying mathematical theories. And in 1959, Cerinonus published the result of elementary definability. Logicians seem slow in recognizing Cerinonus theorem as a basic tool in the theory of definability. In fact, among many papers we quoted in our report here, we surprisingly see very few that mention Cerinonus theorem. Very basic. You can say that this theorem is a kind of completeness theorem for definability theory. If something is not definable, you can have automorphism which proves this. So for this sound. We tried to extend the Cerinonus result, keeping the isomorphism and at the same time not extending the structure. So to have more broad result, but to keep structure the same. It happens in a pretty straightforward, simple way. It comes out of Cerinonus, the various Cerinonus theorem, the following definition. We can call structure or space upper complete if it all its elementary extensions are isomorphic. Clear. Omega, of course, is a simple case of this definition. So in this case, naturally appear the theorems that for every structure, its definability in the case of upper complete structure, the lattice of closed supergroups of automorphism and upper complete elementary extension are the same. So in this case, we can have upper complete structures, and we can have structures who are elementary equivalent to this upper complete case, upper complete structure. By itself, it cannot be not upper complete, but the space is the lattice of spaces is the same as this upper complete case. So in this case, we have this automorphisms between two structures, lattice of subgroups and lattice of relations. And this was used to find out what is the lattice for integers with successor. So we have rationals at its homogeneous structure. Integers, of course, are not homogeneous, but of course, a very basic set in mathematics. And we can describe all its subspaces. And you can guess that this lattice is infinite. Here it is written, its elements. It's pretty simple. The first one is the distance between x1 and x2 equals to some n, to 2, 3, etc. And the last one is the difference is just n. So the second one, you can clearly read what is written there. So the x1, x2, and x3, x3 are the same, have the same direction. And that's all. There's nothing more subspaces than all this, with, of course, series with n. And we can describe exactly what are the lattice operations on this, and it's written down there. Of course, with you can guess that it's used the general common. Yes. So then another case. If we consider Q rational numbers with plus, so it also has a infinite lattice. It also was proved by Sergey and me, and I just comment on this picture. On this picture, you can see 6 edges, 6 vertices only, but two vertices here are actually infinite series of vertices. Just it's a graphical representation of it. So one of these black dot corresponds to all the relations in the form y equals r multiplied by x. So just linear transformation or 0. And there is, of course, an infinite series of this, and all these are in some nice lattice operations, which are exactly the same, isomorphic to multiplicative subgroups of rationals. And under each of these space is another space, which is this one multiplied by r, or set of this multiplication, as I said. And what is written there? Plus minus x plus minus y. So this is the complete, again, lattice in the case of addition of rational numbers. It's infinite, as I said before. Next, the next is that not in the case of what was called upper complete, but we tried to find a formulation of Svenonius theorem in a more general sense for every structure, but to construct just one possible extension for this, which gives which have the same structure of groups, of subgroups, of supergroups. Here is the definition. We consider as a new domain set of all sequences of original domain, say U, universe, and then we define almost, say, automorphism, almost preservance of R, if it preserves R on every vector besides some finite piece of this. And permutation which almost preserves the definability space, so all elements of the definability space, we call ultimate automorphisms. And so here the theorem in this ultimate automorphism case. So the definability lattice of finitely generated spaces is anti-isomorphic, Galois-isomorphic to the lattice of groups of ultimate automorphisms of spaces. What is important here? That we constructed just one space and one set of groups of this, not like in Svenonius theorem. In Svenonius theorem, you have different extensions, elementary extensions for different relations R. So Yes, we get this this version of Serinow's theorem. So now a few few concepts evidently appearing along with the line of study of indefinability theory. One of these appeared in 1966 when Elgert and Rabin wrote his many times quoted papers on extensions of second and first order monadic effect order theory of successor or generalized successor, few successors. And they posed one problem there, that there exists a structure with maximal decidability theory. In our terms, the definition is that the theory of a space is decidable and it cannot be extended to any bigger definability space with decidable theory. It was many attempts to do something here, but some of the interesting results was obtained by Sergei Sopronov, my author here. I will not read out all the details here, but just say that it gives an answer to the problem of Elgert and Rabin in the case of monadic language instead of first order language. There were many results along this line, and for example, Alex Bess and Patrick Sigelski considered a situation with expansion of constant only, and I received kind of a question that there is some structure which has an undecidable theory if you add any constant to this. Again, we can consider other notions of this definability here, and I don't have enough time to explain anything about his, but just one thing is that interesting how the height, quantifier height, can be associated with definability. So can be different correlations between these. Also, I will not perhaps go further. One more interesting, very kind of natural, at the same time, very exotic notion was given here, but Andrei Muchnik, who proposed a notion of self-definability. Notion is pretty simple. Can we use a free constant, free predicate constant, and then to have kind of in the same structure or in the same space, define the property to be definable. It's written here. Andrei invented this in connection with Pressburger arithmetic and some result of Cobham and myself for definability in automata theory and Pressburger arithmetic. And he found a very interesting proof of our result. But also he proved that the space of natural numbers, of addition of natural numbers, is self-definable. And it has kind of looked like very rare. So another evident option is homogeneous structures, but we don't know actually anything interesting more than this. So now the major part of my talk, which is open problems. I have some 10 minutes more, I believe, to discuss it. And just examples I mentioned here. Elgert Rabin, 1966, asked if there are maximal decidable definability space. In fact, our interest to this very field of definability was provoked by Albert Muchnik, very well known in recursion theory, name and the father of Andrei Muchnik. And he referred to Pyotr Novikov somewhere in 1975, saying that Novikov asked about the definability structures of integers and plus. We started to work on that and then found that it's not too simple. Another example is Thomas' conjecture. It was presented before. One more Andrei Muchnik was said. Another is about the quantifier height we mentioned before. But let's try to consider as a general situation. So what actually we try to investigate? We investigate spaces or structures and prove some of their properties. Many properties, many cases of special structures. Another approach is to find more examples of spaces with given properties. For example, more self-definable spaces. And then to prove or refute some properties of class of structures. For example, Thomas' conjecture was about this homogeneous, or you can reformulate for omega categorical structures. And in fact, we can say that even there is some meta-meta problem, so which I propose for our community came together in this conference and perhaps interested in these subjects much broader, like many of the participants of the whole today's movement for definability theory. So to find among all this big pool of problems with different languages, with different structures, with different questions, what are the most interesting possible to decide, to resolve, and useful for other cases. For example, Badirsky and Pinsky placed a couple of problems here, again, connected with Ramsey property. We didn't have enough time to discuss the Ramsey approach to these problems, but it's pretty natural and gave some new results here. But then again, more questions on there. These are classes of languages. Again, not spending too much time, but just to see that the list is pretty long here. And classes of structures. Again, homogeneous finite range structures we started with, but in fact, subspaces or homogeneous structures could be not homogeneous. And what are the properties here? Again, you can consider functional symbols and other cases as is written here. And then specific spaces. For example, as I said, we described all subspaces for all the lattices for Q plus and less. Plus. But there is no result about what will happen if we add less. You can guess that it could be something simple, but as you saw perhaps from the previous example, the situations were not sometimes too simple here. I told about Z integers and +1, and I said nothing about Z and less. Again, it's not clear what is the answer there and how to prove it. Again, it's okay with Z +1, but what happens with N +1? Again, you can try to do something here. To go a little bit to the graph cases, let's consider a kind of, could be said, infinite tree or something, and a non-directed infinite graph without cycles with all the vertices of degree 3. What's happening here? And many other pretty simple and natural cases can be considered, and the issue, all of this, some of them can be homogeneous, but many non-homogeneous structures, perhaps all of them having infinite lattices, and what will happen there. So I propose to start what can be called notebook on unsolved problems in definability theory. We have a good tradition in Russia of the situation for group theory and semi-group theory and rings theory. For example, in group theory, it was Kaworka notebook, and many additions were made to there. So I propose to make the notebook of this definability theory. And I think that with this talk and some other talks I'm giving this summer, and perhaps we'll write to our colleagues, including these ones mentioned in this presentation, to propose more interesting questions here. As I said, existential problems, as I said, this one specifically interesting for that of this reason. And I believe we'll have the week arithmetic days next summer in Moscow in 1 year from now or a little bit later. And then will be a problem session for this definability theory, and we'll present the really first edition, considering today's presentation as the pre-edition, pre-notebook, before this first edition will appear. So that's the end of my talk, and thank you very much for participating.
Yeah, thank you very much for this very interesting talk. And now I would like to start the session with questions.
I take it that when the structure gets a little bit complicated, you don't expect to want to do anything of this kind, right? In other words, for example, suppose a structure has a pairing function on it.
Yeah, so your question is if you have some free pairing or something like this.
Yeah, I'm trying to figure out these nice results where you actually really get to say something depend on the structures being pretty tame, pretty nice. In other words, if you don't want to look at the universe of sets with epsilon or something like that, you want to look at structures that are much more manageable. And I was just wondering where the cutoff is. So if there's a function f from d squared into d that's 1-to-1 onto, for example, I would assume that makes sure that you don't have anything interesting like this to say.
Yeah, yes, in fact, that's true. The structures we consider, the spaces we consider, are very simple in, say, arithmetical sense or something, of course so. But at the same time, it could happen that some more sophisticated structures can have pretty simple structure of these definability spaces.
Oh, okay. Well, give me an example of a more sophisticated structure that does have that.
For example, again, how to consider. For example, if we have arithmetics, of course, at the very beginning, if we consider again the subspaces like space of plus only, of multiplication only, there will be nothing to say about them. They're very complicated.
Okay, the ring of integers, no good, right?
Yeah, but then you have a hierarchy of arithmetic sets, and it's more regular in some sense.
So what can you tell? All right, let's just take the ring of. Let's take the ordered ring of integers.
Yes.
And you ask and you want to prove something interesting about that along the lines of this talk. What happens?
Yes, exactly. You can on this previous screen, it is started with ordered ring of rationals.
No, that's the group.
It's a group, yeah.
I'm talking about the ring. Okay.
You say that you have again the
multiplication and addition.
Yeah, addition. Again, if you consider its module plus and multiplication itself, you can consider something different. But in fact, if you take this ring, you should describe what happens with integers and multiplication only, of integers and addition only, integers and order only. But even for integers and order, it's not clear, it's not known what will happen. So that's
okay. So I'm suggesting maybe there's a series of results that say give sufficient conditions that this is horrible. In other words, that you wind up with a gigantic mess. Maybe the lattice is is some horrible properties or something, or maybe they're all so horrible that they're isomorphically horrible. I mean, I have no idea. I don't have a good intuition about this. So what's missing, what I don't see in this talk is this negative results that under a large number of circumstances, there's nothing to say.
Yes, first of all, of course, you should think about what is nothing to say. It's
right.
Like anything can be embedded or something like this.
Yeah. I mean, that's your that's what I was expecting to hear. That's all.
Yeah, it's a reasonable set of questions. So that was the starting point for the further discussion. How you can define the irregularity, how you can define that it's nothing is clear, because it looks very sophisticated. That's okay. So how do you define this? Yes, it's one of these problems for the new, you say, notebook of definability. Yes.
But I also noticed that these ones on that page are all countable. So if you look at the reals, various structures on the reals, I don't see any results here.
We limited ourselves with the countable case. But for example, reals, say order on reals is elementary equivalent to order on rationals. The point here is that there will not such a nice structure of groups of transformations for reals, because as you see, we have, for example, the cut with irrational number.
Right, so you don't have any cuts in the reals, so that changes the answer.
Yeah, so there will be a little bit again twist here. We have the answer, but the technology, if we not go through rationals, would be a different one. So
it'd be nice to see also the field of complexes here.
Yeah, of course, and we can to have countable. We can have again these algebraic numbers, etc. Yes, and some hint here can be connected with again self-definability, but again it happens to be very rare situation. Yeah.
There's another question by Professor Solovyev.
I have a small question, maybe naive, but it's by analogy sort of, because you mentioned different hierarchies of automorphism groups and so on. So basically, I considered not so long ago automorphisms of types. For example, first order types, second order types in type theory. And there are some interesting groups. Do you think that some sort of use may come from it, similar to, like, I don't know, all this invariance, Galois theory, and things like this, if it is developed in a more sophisticated way?
Yeah, my feeling, yes, that could be connection. In fact, in some cases of structures, yes, I think it's a good thing to think about. Yes.
Anyway, I discovered that, for example, any finite groups can be represented using second order types.
Yeah.
Okay, so thank you.
Yeah, thank you. Are there further questions? Well,
There was something that I came across that I found out was already known, but it's kind of an amusing thing in definability theory. And maybe a lot more could be done with it. I got interested for some reason in the following question. Is there a structure with a unique undefinable element?
Unique undefinable element?
Yeah. Is there a structure with a unique undefinable element? And I had trouble proving this. I managed to prove this, but then I found out this was actually known. I don't think it's very well known. This was published, I can't remember his name, a senior logician now. Let me think if I can remember. I can't remember his name right now. Anyways, but you know, I mean, this leads to a bunch of questions like, can you have exactly, I mean, I don't know if these are any harder though. Can you have exactly 5 undefinable elements? You know, things like this. I just wonder if you'd ever come across this, because this does exist. It was published some years ago. I wasted some time rediscovering it.
Mm-hmm.
You ever heard of it?
Not really, and perhaps there is a kind of different notion of definability, but it's very important to find out. And I believe we'll try to do it even without exact reference, but just looking.
Yes, this was just straight. I think it's finite relational type, and regular first order definability of the usual standard kind. I think, you know, so there was nothing strange about it. Yeah, I think that's what it is. Yeah, I can. Meanwhile, I can look up who that was. But it sounds like I've gotten you a little interested in it.
Yes, very, very much. So if you find it will be really helpful.
Yeah, I will find it. I'll send it to you.
Okay. And really, I enjoyed your questions. So it really extends my feeling of the subject. Thank you very much.
Thank you for the talk.
Are there further questions or remarks or whatsoever? So I do not see further hands, so to say. So I would suggest to close the session for today. It was a very long session, a very nice